Now, I'm going to use my cylinder formula. I'm already using that. And again, this is the version of cylinders where I do not care whether the base is a circle or not. So I know that the volume of this particular slice here, this is a cylinder. The area here is my a of x function. And then the height of this cylinder is what I'm going to call delta x. So remember that delta x is the width of my x intervals. We haven't had the chance to talk about this together, but I expect that you've seen stuff like this in previous calculus classes talking about the Riemann sum formula. So again, my volume of each slice is going to be my area function evaluated at some particular coordinate, xi. Perhaps we're using left-hand endpoints, perhaps we're using right-hand endpoints, perhaps we're using midpoint formula. But whatever that sampling method is, I'm expecting to see area of the slice times width. And width here is my delta x. My volume for the whole region will be, well, let's add up my slices. And the more slices that I get, the more accurate my approximation will be. So when I only have 1 or 2 slices, I don't get a very accurate picture. As I take 10 or 20 slices, it looks a little bit better. As I take 10 or maybe 20, excuse me, maybe I should say 1,000 and 2,000. As I take more and more slices, my volume function still looks good. But to truly get the accurate volume of the solid, I need to take the limit of the Riemann sum. And in the limit of the Riemann sum, my Greek letters are telling me my approximations. My Greek letters are telling me the macro level behavior. If I'm only allowed to take finitely many slices, then that is a Riemann sum. But integrals, at least I like to think about integrals this way, integrals are nice and smooth. They allow me to take infinitely many slices. So take as many slices as I need between the coordinates x equals a and x equals b. The area for each of my cylinders is still a of x, but now the width is my dx, my infinitesimal dx. And since my Greek letter D turned into a Latin letter D, my Greek letter S has turned into a Latin letter S. Such wonderful little surprises we hide in our notation. So this is the volume formula that we will be using again and again and again, that the volume of this region from A to B is, I'm integrating from A to B, the function a of x, dx. Now, it's very important that these slices are slices that are perpendicular to the x-axis. Let's see that in the picture again. So here we have a sphere, and we have placed it directly on the xy plane, sitting at the origin. And we're going to slice this for every x. I'm going to take my knife, I'm going to slice this thing, and I'm going to see the shape that I get. Well, all of those slices will be circles. So let's actually integrate this area function to calculate the volume of a sphere. We picked a sphere because we already know its volume formula, but that'll let us double check that the integral worked correctly. Lets us fine tune our method.